Hi, I'm Kyle Snow. I'm from Lawrence, Kansas. I'm going to be a sophomore in chemical engineering at Kansas State University, and my research is synthesizing platinum nanoparticles by use of alternating voltage reduction and oxidation. So the basic overview of this research is, well, the big picture would be to create platinum nanoparticles which can be used in fuel cells for like hydrogen fuel cells, using water and oxygen to combine to get energy, which could be used in our cars, maybe hopefully one day to replace gasoline, which would be a much more efficient and environmentally friendly way to drive or get energy for heating our homes or other things such as that. So the goal with this project is to create platinum nanoparticles that are easily controlled size and shape. Hopefully we would like to get them to be consistently around 10 nanometers in size. And it's really important with nanoparticles that the size and shape is just about like almost exactly where we want to be. It's really hard to control, but we want it to be as accurate as possible because when you get down to a size that small, the size and shape has a very large effect on how efficient the nanoparticles are as far as catalysts go. We would like them to be as efficient as possible. All right, so here we've got my two platinum wires. They have pieces of plastic tubing, really small, slipped over them and then glued together with glue from a hot glue gun so that they are held about this far apart from each other. And then in my reaction, they will be held right here and then dipped into this solution, which is a solution of water, potassium sulfate, and polyvinyl pyrrolidone. The polyvinyl pyrrolidone acts as a stabilizer to make sure the particles stay the size that they are when they're created, because otherwise they like to clump up and become bigger than they should be. And so in my reaction I'll be dipping these guys down into here and attaching these wires, which provide the current from this function generator here, which allows me to control the voltage and frequency. And that's what it'll look like. All right, so this is my function generator. This is what's supplying the current to my platinum wires. And it allows me to tune the frequency in hertz of the current and the amount of voltage with this knob here. So for this test that I want to run, I think I'm going to want it at 10 hertz. Sometimes it can be hard to get precise. Then to observe the voltage, I'm going to use this voltmeter and hook up my wires. And right now it says about 5.94 volts. I want it slightly higher than that. We're at about 6 volts. That looks good. And now it should be ready to start my experiment. Right now I have my reaction set up and running. I've got about 6 volts current running through at 10 hertz frequency. And the voltage is alternating, so there's both oxidation and reduction occurring on these two platinum wires. And I think you can see they're bubbling and bubbles are rising to the top from that. This could take anywhere from 10 to 30 minutes depending on the, or even an hour depending on the parameters of the experiment that I have set up. And it looks like this one is starting to see some color, but it might take another 15 to 20 minutes before the whole solution becomes dark. All right, so this is my finished nanoparticle solution. Okay, so the one difficulty of using this method for making nanoparticles is that in our solution to start with, we have to include a salt as an electrolyte to help carry the current through the solution to make our nanoparticles. But once the solution is made, this is what it would look like when it's done. The problem is, once it's made, we don't want the salt in there anymore. To actually look at the nanoparticles under a microscope, we need the salt to be out of there. The salt kind of obstructs the view of the nanoparticles, and also for the applications that we want these nanoparticles for, we probably don't want any salt in the solution for that. So we need to find a way to transfer this to another solution not containing any salt. So what we want to do is, it's called a phase transfer. We want to transfer this from a layer of our aqueous solution as we have it to a solution that is non-polar, like toluene or hexane. So I can set that up and show you that right now. So I'm going to pour in my nanoparticle solution. Now here's my non-polar solution. So what you'll see is you can easily see the two separate layers of solution with the color on the bottom. The two liquids don't want to mix, but on this hot plate here, I'll put in a stir bar. If we can heat this up and stir it, so far for me this has taken about 24 hours to do. Over time, the nanoparticles will eventually dissolve into the solution on top, which is hexane in this instance. And so when the solution, when the nanoparticles dissolve into the hexane, the salt will not follow. The salt will stay in the aqueous solution on the bottom. And it's kind of cool because you can see it happen. Afterwards, you'll see that the color has moved to the top solution, and the solution on the bottom will have, it'll be clear. You can tell that there's no nanoparticles left in it. So you can be sure when you've done it right and when you've done it wrong. And then afterwards we will separate the two solutions so that we can keep the nanoparticles in their new hexane solution and have them by themselves. So we're measuring how much light this sample will absorb at certain wavelengths. And depending on the results we get from this, will tell us if the solution we made is good or if it's bad. But this only really gives us a rough estimate. To get a better idea of how well our particles are made, we'd have to take them over to Hill Hall and put them in the TEM, which stands for Transmission Electron Microscope. But that's an expensive machine that we save for only our best samples. So we want our second cuvette to be filled with this, so we can get a comparison. The machine will give us a comparison of start to finish of before the nanoparticles and after the nanoparticles. All right, should be running in a couple seconds, but it's kind of a slow process. It might take 2 or 3 minutes. But you can see starting at about 800 nanometers there, and it's rising upwards, which so far is what the spectrum would look like for platinum nanoparticles. Here we can see it slopes upward a little bit, which is really, it's kind of a boring spectrum, but that's what platinum nanoparticle solutions tend to look like. So looks like we had success with this one. I feel extremely privileged to be here. I'm gaining a lot of experience that I don't think I definitely wouldn't have unless I got this opportunity. And I feel like I might be a little bit ahead of the rest of the people in my classes when I go back to school in the fall, just from this research. And I think it's really nice to get started early and kind of get a feel for what research is like. And so far, I'm loving it. It seems like all the staff are really unique and easy to work with, nice to talk to. Yeah, and they've been nothing but helpful to me, and I'm really glad that they could make this happen.